So this process is biomass gasification. We take waste wood, we chip it, and the product I use is about a 2.5 inch minus type of product. It provides the necessary surface area that I need in my reactor. I don't use something that's too big. It causes problems with my material handling systems, or something that's really, really small and fine, like a sawdust type of thing, because that doesn't provide me any useful surface area. So this is a chip product. It's material that currently I brought with me from Montana. But we have our second drying bin full of local product with pinyon juniper material that was chipped here on site, and we'll be running that shortly. So the system has 2 feedstock bins. One, as I said, was filled with dry material. This material is dried to a moisture content of about 11%. Probably this was 40% plus when I loaded it. And I have a second feedstock bin filled with this local material that looked to be about 35% moisture content. And so when we process this one dry bin, we recover the heat, and we use that recovered heat to dry the moist bin. And then when we're done with the dry bin, we have a new dry bin that we swap the process, fill up the empty now with moist material, and repeat the process. In any kind of woods handling system, the big issue is solids handling. I have a system that's configured, optimized for wood chips. You can optimize them for pellets, or somebody was mentioning cherry pits. You can optimize it for almost any type of biomass, but once you optimize it for that particular biomass, obviously you've reduced your flexibility. So we've tried to make this as flexible as possible, but it's still optimized for wood. We've used some pretty ugly slash in it. We've had clay, rocks, metals, all sorts of things go through it. So it does a fairly good job of handling it, but still, if we were to switch our feedstocks to, say, pellets or cherry pits, as one of your colleagues recommended, the clearances in the auger systems are too great, I think, to conduct that material efficiently through the system. So most of my headaches are in the front part of the system with handling, drying, conveying wood chips into the reactor. This is the gasification reactor. It's basically just a big pipe, and the pipe is full of wood chips. There's about a 6 to 8 inch layer of fresh wood. There's a small flame front at the bottom of that, and the whole rest of the length of that reactor is full of hot char. The char is about 800 degrees C, and we control that through differential injection of oxygen. That's what these rings are around this gasification vessel. So I monitor temperatures in 5 different levels, and if I don't like what I see, I can inject additional oxygen to raise the temperature, or extract or limit the oxygen to reduce the temperature. So that's my method of process control. There's a number of reactions that occur in a gasification process. Some are endothermic, some are exothermic, so the temperature profile through the reactor is not constant. It's high, and then it goes a little bit lower, then it comes back high again. But we exit at about 600 degrees C. That's too hot to throw into an engine, so we cool it down. The heat exchangers on the other side, we'll take a look at that in a minute. We cool it down to about 50 degrees C. Then we take that cooled gas and we filter it in this baghouse filter system. It's a simple system. There's just 4 individual inverted 55-gallon drums that have filter bags in there. The gas is entrained with a fine char pellet. This is what the char looks like. Most of it's very fine particulate, some of it's a little bit larger, but that's entrained in the gas. It's blown through the tube side of the heat exchanger and is extracted out at the filter system. The char is collected in the bottom of the filter system, and there's an auger that augers this material out, and in the back there's a larger drum that contains and collects this char. As I mentioned in my spiel before, this is called a biochar. It has properties that it can be used as a soil amendment. So we are working with researchers at the University of Montana where they reapply this material, and they're actually using it in that particular instance as a defense against invasive species. They find that an application of this char around invasive species helps mitigate some of the chemicals that the invasive species give off to give it unfettered access to the land. So by removing some of those chemicals, the natives are allowed to crowd in and perhaps control and manage the invasive species. So if we want to walk around the back here, this is our control area where we have our PLC. You can see it up there on the big screen. This is my assistant, Mike Bergman. So we monitor our operations here. We have a webcam that's looking down at the gasification system, so we can see what's happening in the top of the gasifier just by our position here. This is the barrel where the biochar is collected. Again, this material is being examined for commercial uses in agriculture, or as I said before, in potential management strategies for invasive species. Let's walk up this way and we'll come back down. So this is what we loaded up. This is the local material that we loaded up with yesterday. This is in the process of being dried in our second feedstock bin. And when we run out, probably later today, with the primary bin, we'll switch over and start using this stuff. I find that if I have a lot of needles, I get clinker formation. There's a lot of phosphorus. You know, most of the minerals are concentrated in the leaves and the needles, also the bark. If I have a high percentage of those materials in my feedstock, I tend to have more maintenance issues because they form clinkers. They clog up the bottom of my gasifier and it requires me to take the system down and clean that material out. From the other side, I mentioned we had the gasifier. The hot gas comes out, it goes through this heat exchanger. This heat exchanger is just a tube and shell. The hot gas and the in-train char goes through the tube side. We just use ambient air as a coolant. The ambient air comes in the middle of the heat exchanger and is pushed out to either end. At either end, the hot air is recovered and is traveled overhead back into the bin area, where I can choose which bin to dry it with. We have three potential sources of recovered heat. First is the one I just showed you, this heat exchanger with the hot gas. The second one is in the engine compartment. We have a spark engine that's running over there. We'll show you that in a minute. There's also a heat exchanger in there, and I can recover heat off the exhaust gas. I can also recover heat off the coolant. So I have three potential sources. Right now I'm only recovering heat off the hot producer gas, and that gives me a thermal efficiency of about 70%. If I recovered heat from all three sources, that thermal efficiency would go north of 90%. This is basically the control system. This is where all the sensing elements and the PLC is located, the computer. This is a portable unit, obviously, and it's been especially ruggedized for portable travel. However, I find occasionally, especially on access such as this, bouncing down the road, any number of these pliers can pop loose. And then you have probably a 1 to 2 day troubleshooting session trying to figure out which bloody thing went wrong and how to fix it. So there's always issues with these systems, but this has performed remarkably well. And then here is mostly an off-the-shelf gen set. We're using a Chevy V6 that can run on propane or gasoline and producer gas. It's been modified. And I'll show you the engine side, and then we have it attached to a generator. This system produces 25 kilowatts of electricity, and I'm recovering about 200,000 BTUs per hour of waste heat. Chevy V6 operating on wood gas. "25 kilowatt electricity. 480 volt three-phase electricity is being produced by this. Since we don't have electrical load right here, we're only running our parasitic systems, which run between 2 and 4 kilowatts. So we have additional gas that's left over. What we do is we flare it up this top in the stack. We do have an onboard transformer, and I can transform that 480 three-phase into 208 three-phase, and from that we can get 120 single-phase, which would power normal household appliances. We've used this system before in remote powering applications. In Missoula, Montana, we're coming into our festival season where we often have every weekend some kind of music festival downtown. And they often invite me to come down and run their sound stage with the output from the system. It's a difficult load because it's a very dynamic load. This system would prefer to see a nice steady grid load, but we have been able to manage it. We get on sound stages anywhere from a 5 kilowatt usage up to a 15 or 17 and back down. So in order to follow that system, you need a fairly flexible, robust generator. Sometimes if we have too big of an excursion, it will fall down, but normally we can follow those kind of loads. Yeah, so a couple other examples of this technology that I'm familiar with. There's a similar system. It's a little bit larger. This is 25 kilowatts. There's a system in California that's twice as large. It's 50 kilowatts, and it's on the property of an organic walnut farmer. So this walnut farmer has his back 40 full of spent walnut shells, right? So he's bought a big one of these things. He's converting that waste into electricity and heat. He uses the process heat for drying his product and the electricity for running. He's not completely off grid, but he's close to it. Another option or another example is the U.S. Army. Overseas, they've deployed a couple of these systems that are contained in shipping ISO containers. 2 or 3 containers the system is contained in, and they use spent trash. They shred up paper, plastic, cardboard, all those materials, and they compress it into a plug, a pellet type plug, and they gasify it and make their own heat and electricity, and they power a tactical quiet generator.